So we will discuss now the role of the pKa values in helping us write equations, acid-base equations, determining where the equilibrium will shift, and of course, with other features like will this acid react with this base or not? So you will learn about that. Now, a little bit from Gen Chem, a little bit from Gen Chem. If you recall from Gen Chem, you had uh, must have studied about, or Gen Chem 2, about acid-base equilibrium reactions, and it would look, for example, something like this. So you have an acid right here. You have water would be your base. Again, it lost its proton, so this is now the conjugate base. Let me write a little bit smaller because I need the space below. And of course, this would be the conjugate acid. Now, if you recall, if you wrote the equation for the equilibrium constant, it was the products over reactants, the concentration of the products over the concentration of the reactants. So it would look something like this. You would take the concentration of A minus, or let's start with H2O actually, because we're going to need that. H3O, I meant, times the concentration of A minus divided by the concentration of HA. It doesn't matter in what order, by the way, over H2O. So this would be the equilibrium. Now, for dilute solutions, H2O is a constant. So if you recall, you actually had to look at the acidity constant, which is Ka. It would be Kq times the concentration of water. So it would be a constant. So because think, it's a 1. It would actually become simply the H3O plus the hydronium times the conjugate base of the acid over the acid, HA. Now, this is a measure here. Okay, this is the measure. Ka can be used to indicate the strength of the acid. If you have more dissociation right here, okay, this tells you that you have a stronger acid. So if the denominator is high or it's a large number, then you know, and the numerator, if the numerator is a large number and the denominator is a small number, then you actually have a high value. But nonetheless, what we need to know, we're not going to do any calculations in this class because we really don't have any time for this. What we need to simply look at the pKa. So this would give you numbers like, like 10 to the negative, etc., right? Like 10, -10, -11, -9, -6. But we don't want these numbers right here. So what we want the pKa. So the pKa is simply the negative log of the Ka. And what's nice about that is that it gives us small whole numbers, right? So if we look down here, the Ka would give us these values, but the pKa would give us again whole numbers that they range from about plus for the typical organic acids from +5 to +50. Now, here's the important piece of information that you need to remember. All of that is like I said, is important. But what we need to know, okay, is that the more readily a compound donates a proton, the stronger the acid. And this results in the lower pKa. So if you have a lower pKa, you have a stronger acid. So Again, that's the idea here, is if you have a stronger acid, then that corresponds to a low or a small pKa. Very good. Let's go down here and talk about the typical ones that you need to know. So very strong acids. So Appendix A is in your book, and I'm going to show you one that I like to use. It's much more thorough. Very strong acids, they tend to have a pKa of less than 1. Moderately strong acids, they tend to have a pKa of, from 1, let's say, to 5. So these are approximate ranges. Weak acids, they tend to have pKa of 5 to 15. And extremely weak acids, they tend to have pKa's larger than 15. So once again, these are approximate ranges that will help us understand which acids are strong and which ones are weak, which ones are in the middle. You will see this a lot really throughout Organic 1 and 2. Now, I'm going to show you this handout, but before that, well, actually, let me show you, and then we will. One second. Right here. So you have the pKa chart. It's very, very inclusive. We're going to use it in this lecture, and it's on your, it's on Brightspace. So make sure you examine it. It's going to give you the pKa, and it's going to give you the conjugate base. So again, the range is found here. It's very useful. Now, of course, it cannot include everything. There are over 20 million organic compounds, but it should be good enough for the majority of the compounds that we will do in this class. Now, if there's something missing, I will let you know. If you can't find, you can look it up. But here it is. It gives you the pKa. So look at sulfuric acid. It's -10. It's extremely, extremely strong acid. Hydroiodic acid, -9. Now, of course, you go to things like right here, like alkanes. They're incredibly, extremely weak acids. So let's look at some ranges here that we need to know. Now, for you, even if you do not, remember or use that sheet, you should remember these ranges. Now, these are ranges that are found on, like, again, on the PCAT, the MCAT, some of these exams that they won't give you actually the sheet. So it's worth investing time into knowing these. But let's look at them. Now, these are what we call protonated, right? Protonated oxygens. And what they have is they have a plus charge on oxygen, and oxygen has 3 bonds. So it's incredibly, incredibly acidic because it wants to lose that proton. But we'll get back to that. So basically, the pKa of any of these oxygens with the 3 bonds, with R, by the way, we mean, any, like, if it has a carbon, any carbon chain, these have a pKa of less than 0. So they're very, very, very acidic. And once again, they are very strong acids because the oxygen has 3 bonds. So I'm going to write this on the side because it's very, very critical. So oxygen with 3 bonds. So it's a positive charge. Again, not allowed. So that's a positive. Okay. The next ones have a pKa, anything what we call, these are carboxylic acids. They have a pKa of around 5. Any ammonium, what we call them ammonium, nitrogen, well, it's not ammonium, but could be an ammonium ion or cation. Anything with nitrogen that has 4 bonds, and those are organic chemistry, are typically either hydrogens or, again, carbons with chains in them, like carbon chains. They tend to have pKa's of around 10. Now, alcohol and water are very close, so they tend to have a pKa's of 15. And alkanes, those are alkanes, or basically carbon with hydrogens attached to them. Those are extremely, extremely weak in terms of acidity, and they tend to be close to 50. Now, this is not a difference of, 35, let's say, numbers between it. If you go back to the pKa, it was a negative log, right? So it's actually based on the power of 10. So the difference is incredibly, incredibly huge. We're talking about the difference between this one and that one is a difference of 10 to the 35. Can you imagine how large that number is? That's larger than Avogadro's number. So of 10 to the 23. So we would like to, again, look at an important or thing to say here is that these are extremely acidic. These are moderately acidic. These are weakly acidic. And these are extremely weak acids. Let's put it this way. Very well. Again, an acid that readily donates a proton is a strong acid that actually forms a weak conjugate base. A strong base that readily accepts a proton forming a weak conjugate acid. So these are very important trends and patterns to learn about, because again, you will actually save yourself time by understanding these patterns rather than memorizing every single case. You cannot do that in this class. You have to generalize and of course pay attention to some very, very tiny exceptions.